Hello, my name is Pablo Herrero and I'm going to speak about barium tagging in the next experiment using fluorescent bicolor indicators, or FBI for short, and I will show our latest advances using surface science techniques, so let's take a look. Barium traces unambiguously the double beta decay of its mother isotope xenon-136. Therefore, its detection could be crucial to demonstrate the Majorana nature of the neutrino. Here's how it could work. Next, TPC reconstructs the ionization track of the two betas. Meanwhile, the barium drifts toward the cathode, where it's captured by a molecule on a monolayer. This molecule then changes its emission color, yielding a signal for barium that we can detect using fluorescence microscopy, scanning the region indicated by the barycenter of the track. The electron track and the barium signal are in delayed coincidence, so the expected background for this process is zero. Now let's talk about the color shift. In a previous study, we deposited FBI on silica pellets and evaporated barium perchlorate on them in a vacuum chamber. The control sample with no barium emitted only green light, whereas the sample with barium emitted light in the blue region. This was the proof of concept of our experiment. However, concern was raised as to whether the humidity of air affected the fluorescence. Therefore, we took a different approach. We sublimated FBI in ultra-high vacuum on a gold single crystal. Then, barium chloride, and we characterized chemical and conformational changes induced by the capture of the ion. For this, we used two surface science techniques. The first one is X-ray photoemission spectroscopy. XPS revealed chemical changes. As we increased the dose of barium, the oxygen 1s core level shifted toward lower binding energy. Oxygen is the main agent capturing the ion. This result agreed with the only other existing study of crown ether chelation on gold in ultra-high vacuum. Moreover, we saw the same shift using copper or ITO as substrates. The second technique was scanning, tunneling, microscopy and spectroscopy. Again, FBI was evaporated on gold in submonolayer regime, and single molecules were imaged. After depositing barium, the structure clearly changed, proving unambiguously that it had captured the ion. The HOMO-LUMO gap shifted in the same trend as the light absorption after capturing barium. We also imaged the fluorophore part of the molecule in high resolution to help identifying the overall structure. This study proved that FBIs can capture barium in ultra-high vacuum and undergo chemical and conformational changes that yield the fluorescence shift. This sets a promising path for developing a barium tagging sensor in NEXT. Thank you very much.